I hope you enjoy this hero's journey into the realm of philosophy, psychology, and physics. If you want to help me create more content like this, please subscribe and consider sponsoring me here on YouTube. I also want to thank the Platonic Mystery School of the Divine Infinite Being for sponsoring this course, and you can check that school out at divineinfinitebeing.com. Quantum mechanics, particle wave paradox. So this is the next step in the history of physics after Isaac Newton. So it started with Isaac Newton's mechanistic cosmology of the rigid three dimensions of space and the linear timeline, with little ball bearings of insentient soulless matter enduring in that framework. That was 1687. Then, in 1905, Einstein introduced a special theory of relativity based on the absolute speed limit of light. He realized that space and time must be malleable. In 1915, he published his equations for general relativity, which was his theory of gravity, to reconcile the force of gravity with the absolute speed limit of light. Isaac Newton's theory of gravity indicates that the gravitational force travels infinitely fast. General relativity indicates that the gravitational force is the curvature of space-time, and that ripples in that surface of the fabric of space-time would travel at the speed of light, not infinitely fast. The next step in the history of physics is quantum mechanics, which was 1917. Now, quantum mechanics is the theory of the very, very tiny, whereas general relativity is the theory of the very, very large. There's one universe. You would expect there to be one language of physics that describes everything all the way up and all the way down. That's what people thought Isaac Newton's theory of gravity did, but then that was shown to be not the case. However, the problem is that the mathematics of quantum mechanics cannot be reconciled with the mathematics of general relativity. You can't use quantum mechanics to predict what will happen at the largest scales of the universe, and you cannot use the equations of general relativity to predict what will happen at the smallest scales of the universe. So that's been an enormous tension of opposites in the history of philosophy ever since 1927. As we'll see, string theory does mathematically reconcile these two opposing languages of physics. Problem, however, is that the strings of string theory are so small that they cannot be empirically observed with the technology available to us today. Leonard Susskind said it would take an atomic accelerator the size of the galaxy and 1 million barrels of oil a second to fuel it in order to create the wavelengths of energy small enough to peer down at the level of the fundamental strings, which is the Planck scale. So there's a little preface to the drama that we are now entering into with quantum mechanics. So the particle wave paradox. Sometimes light acts like it is made of particles, sometimes like it is made of waves. The same is true for all particles at the atomic scale, such as electrons. Two-slit experiment. All things at the quantum scale act like waves of probability when they are not being measured, observed, and like individual particles when they are. So the two-slit experiment. This is another crucial point to nail down in your mind to have an appreciation of the psyche equals singularity equation. And it should just be fundamental knowledge for every person here in the 21st century. What is the two-slit experiment? So it was an experiment designed to detect whether or not photons, and by extension all quantum particles, electrons, neutrons, and then later they discovered the constituent parts of the nucleus of an atom, like quarks. But at any rate, every entity down at that tiny scale seems to sometimes act like an individual particle, a little ball bearing, and yet sometimes it acts like a wave. Well, which is it? They developed a two-slit experiment to discern. They took a light beam and shot it through two slits in one wall. The two slits were placed very close to each other, very narrowly spaced slits in a wall, behind which was a detector screen, which was covered in gold foil, if I recall correctly, in the original experiment. Now, if the photons are little bullets, little particles, they should go directly through the two slits, just like bullets would. If you shot a machine gun at a steel wall with two slits in it, then the machine gun bullets that hit the part of the wall without the space would just hit the wall and wouldn't go anywhere. The ones that made it through the slits should line up directly behind that wall in two straight bands. That's what would happen if photons are particles. If photons are waves, Then the wave reached both of the slits at once, and then two new little waves would ripple out from each of those slits and start to cascade outward again, and they would interfere with each other. The two waves would ripple into each other, creating an interference pattern. Some places the waves would amplify, and some places the crest and the valley, they would neutralize and there'd be nothing there. So what you would see on the detector screen would be a series of light bands and dark bands. If it's a wave, if the photons are waves, you would see the light band, a dark band on the detector screen behind the wall with the two slits. So that was the experiment, very straightforward. They conducted the experiment, and what they discovered astounded everybody. The photons were always detected by the detector screen as little individual particle hits. But the problem was that sometimes the particles would hit way off to the right, sometimes way off to the left, sometimes up, sometimes down, not directly behind the two slits like bullets should do. After about an hour, they realized that the particle hits were accumulating in the same pattern that a wave would have made if it went through the two slits all at once. The ripple interference pattern, a series of light and dark bands. That was something nobody expected. The detector screen detects each individual photon as a particle, and yet they accumulate just as if a wave had gone through all at once. So that perplexed everyone. Then they decided to add an element to the experiment, and they set up a detector to see exactly which slit the photons went through when they went through one or the other. When they did that, then the photons piled up right directly behind the slits in two narrow bands, just like well-behaved particles. When they weren't watching which slit the photons went through, they accumulated all over the place on the detector screen and eventually formed the pattern as if a wave had gone through all at once. So the implication is that when you are not observing the photons, they go through the two slits as a wave. But then once they're detected by the detector screen, or they're observed by the detector screen, that wave collapses into a particular point. What kind of a wave does that? A water wave doesn't turn into a particle when you observe it. So they came up with the idea of waves of mathematical probability. The mathematical probability for where a particle might appear, most likely at the peak, but it could appear anywhere within the wave, and the waves stretch out asymptotically out to infinity. So with diminishing probability, the particle could appear anywhere in the universe at all. But most likely it's going to appear at the peak, but sometimes it'll appear on the far right or the far left side or anywhere within that wave. That's what a wave of probability is. The most bizarre discovery in physics probably yet, unless you think of the gravitational singularity itself, which is also a quantum particle in the sense that it's infinitely small. So the particle-wave paradox of quantum mechanics was discovered in 1927. Quantum mechanics, waves of probability. In 1926, Erwin Schrödinger discovered the Schrödinger equation that mathematically describes the shape of the quantum waves. Max Born discovered that Schrödinger's equation does not describe physical waves, but rather the probability of finding a particle at any given point on the waveform. If we square the mathematical wave function, it reveals parabolas of statistical probabilities for where a particle might manifest if it were observed, most likely at the highest peaks or lowest valleys. So this is just some of the technical history of the discovery of quantum mechanics. It started in 1926 with Schrödinger's equation, but it didn't come together until the Copenhagen interpretation in 1927. Quantum mechanics, Copenhagen interpretation. In 1927, Niels Bohr, Werner Heisenberg, and Wolfgang Pauli discovered the Copenhagen interpretation of quantum mechanics. Heisenberg discovered the uncertainty principle. The more you know about the position or particle nature of a quantum object, the less you know about the momentum or wave nature, and vice versa. Bohr discovered the quantum principle of complementarity. There exist complementary properties of the same object of knowledge, one of which, if known, will exclude knowledge of the other. The experimental arrangements that determine these descriptions, particle and wave, are similarly mutually exclusive. So, the more you know about the position of a quantum object, the more it behaves like a particle. If you turned on this electron microscope to see which slit an electron goes through in a two-slit experiment or a photon or any particle, by observing it, it acts like a particle. The less you know about which slit it goes through, the less you know about the position of that particle, the more it acts like a wave. It is simultaneously a particle and a wave. Which way you perceive it depends on the experimental apparatus that you use. So that's complementarity. These are mutually exclusive but complementary ways of describing the same thing. At the fundamental level of the cosmos, things behave like particles when you observe them, and like mathematical immaterial waves of probability when you don't. This is a fundamental fact of physics which has been experimentally proved, or at least experimentally vindicated. Nothing can be proved finally. There's always some experiment in the future that might disprove it, but at any rate, all the experiments that have been done so far have vindicated this idea of the particle wave paradox, and we will see how that is also reflected in psychology. Particle wave. Atman Brahman Particle Wave Review. The Gaudiya Vaishnava school of Vedanta philosophy says that each soul is inconceivably simultaneously a particle of personal consciousness, Atman, and an impersonal wave of potential personality merged in an ocean of Brahman. Vedanta philosophy also says that the material world is the inverted and perverted reflection of the spiritual world, like the reflection of a tree on a body of water. That means the laws of physics should mirror the laws of the psyche. The Atman Brahman paradox of the soul is reflected in the particle wave paradox of matter. So here's a fundamental point for this class: immortality and the unreality of death. What is the psyche? What is the soul? It's simultaneously a particle of personal consciousness, Atman, and inconceivably, it is also a wave of probability, Brahman. Brahman is the impersonal side of the soul. Atman is the personal side of the soul. These are complementary ways of describing the same thing. Erwin Schrödinger, particle wave equals Atman Brahman. So this quote will be coming from Schrödinger's book, What is Life? So as we saw previously, Erwin Schrödinger helped discover quantum mechanics. He helped discover the mathematics that describe the wave of probability. He was also an advocate of the Vedanta philosophy of India. And he wrote this book, What is Life?, trying to apply quantum mechanics to biology to discover the unit of biological replication. James Watson and Francis Crick, in 1953, inspired by Schrödinger's book, discovered DNA, the double helix of the DNA molecule. So that is the history of this book, in which he equates the particle wave paradox of quantum mechanics that he helped discover with the Atman Brahman paradox of Vedanta philosophy. So here's his quote. In Christian terminology, to say, "Hence I am God Almighty," sounds both blasphemous and lunatic. But please disregard these connotations for the moment and consider whether the above inference is not the closest a biologist can get to proving God and immortality at one stroke. So continuing his quote, in itself, the insight is not new. The earliest records to my knowledge date back some 2,500 years or more. From the early great Upanishads, the recognition Atman equals Brahman, the personal self equals the omnipresent, all-comprehending eternal self, was in Indian thought considered far from being blasphemous to represent the quintessence of the deepest insight into the happenings of the world. The striving of all the scholars of Vedanta was, after having learnt to pronounce with their lips, really to assimilate in their minds this grandest of all thoughts. And that's also what we are trying to do in this class, to assimilate not only this grand thought of Atman equals Brahman, but to help us assimilate that grand insight, we're looking at its reflection in the particle wave paradox of quantum mechanics. One of the fundamental principles of this entire class is that the laws of physics and psychology mirror each other because mind and matter both radiate from the same transcendental source, the gravitational singularity, which I am equating with the psyche itself. So we've discussed that before. In the Bhagavad Gita, Krishna calls the material world the tree that grows upside down. It's a reference to a reflection of a tree on a body of water. If you look at a tree growing next to a reservoir of water, you'll see that the top is pointing straight down and the roots are at the top. The idea is that the material world is an inverted and perverted reflection of the spiritual world, which reiterates the claim that the laws of physics should mirror and be mirrored by the laws of psychology, which Carl Jung and Wolfgang Pauli both believed. Plato also indicated as much in the Timaeus. But for now, we're focusing on Schrödinger, one of the forefathers of quantum mechanics, and he's pointing out this parallel between the particle wave paradox and the Atman Brahman equation of Vedanta philosophy. I think it's important to note that there is an atheistic school of Vedanta philosophy, most famously advocated by Shankara in the 8th century Common Era. which says that the individual personal soul, or Atman, is a temporary illusion which should be dissolved back into Brahman, this ocean of impersonal spiritual energy. Brahman is eternal, but the individual self is not eternal, says that school of Vedanta philosophy. What I am advocating in this class is the theistic school of Vedanta philosophy, which says that the individual personal aspect of the soul is just as eternal as the impersonal wave nature of the soul. Wolfgang Pauli, particle wave equals conscious unconscious. So this is a quote found in Jung's book On the Nature of the Psyche. He was quoting Pauli, and this is what Pauli said about this particle wave nature of matter and the conscious unconscious nature of the psyche. The physicist would expect a psychological correspondence at this point, because the epistemological situation with regard to the concepts conscious and unconscious seems to offer a pretty close analogy to the undermentioned complementarity situation in physics. So the particle wave nature of matter is a manifestation of the principle of complementarity, mutually exclusive ways of seeing the same thing. To have a complete picture of the object, you have to take into account both of these mutually exclusive perspectives of it. And what Pauli is saying here is that the mutually exclusive nature of the conscious and unconscious mind seems to be an analogy or a mirror reflection of the mutually exclusive but complementary descriptions of matter as a particle and a wave. Schrödinger equated the particle nature of matter with Atman and the wave nature of matter with Brahman. So you can see, therefore, a connection between Atman and the conscious ego, sense of self, and Brahman with the collective unconscious mind, the ground of being, the ocean of potential being from which individual objects emerge. The parallel between the particle-wave paradox of matter and the conscious-unconscious paradox of the mind can be seen by a simple thought experiment. Think of the number 3. Now think of the number 7. Where did 3 go? Where did 7 go? So when you think of an idea in your mind, it pops up in your mind, and all the other ideas that you're not thinking about merge back into your unconscious mind. And similarly, when you observe a quantum particle, it acts like a particle, but when you're not observing it, it emerges back into the ocean of waves of probability. So the mind and the material world, they mirror each other according to Carl Jung and Wolfgang Pauli, so that the laws of physics should mirror and be mirrored by the laws of psychology. And the most fundamental law of physics in quantum mechanics is the particle-wave paradox, revealed by the two-slit experiment. So it is also found in the most fundamental paradox of the human mind. It's conscious, but it's also unconscious. Uniting relativity and quantum theory, quantum field theory. So we're going over the history of a gravitational singularity, and this is the breakdown of quantum mechanics. You don't need to know all of these details with any particular intensity to understand the psyche equals singularity equation, but it's good to have this as a stepping stone in the history of a gravitational singularity. So quantum field theory is the attempt to unite quantum mechanics and special relativity and general relativity. So let me just read this slide and then we'll go over it a little bit more. Quantum mechanics describes 3 of the 4 fundamental forces of nature. So there's the electromagnetic force, there's the weak and strong nuclear forces, and then there's the gravitational force. So quantum mechanics describes everything but the force of gravity, which is why there's this feud between quantum mechanics and general relativity, which is Einstein's theory of gravity. So let me continue reading. Electromagnetic force, quantum electrodynamics. So the field of physics studies the electromagnetic force, which is light, is quantum electrodynamics. So here's a quote from Leonard Susskind. Photons are the ropes that tether the electrons to the nucleus. Orbiting electrons pass photons back and forth to nucleons. So according to quantum mechanics, the 3 forces of nature other than gravity are created by particles passing other particles back and forth between them. Brian Greene, in one of his TV series, I forget which one right now, but I'm picturing it in my mind, he described the electromagnetic force within an atom by showing himself passing a baseball back and forth with another image of himself. And the faster they passed the baseball back and forth, the closer the 2 images of himself, they started being pulled toward each other more and more closely. So the force was created by passing photons back and forth. In an atom, electrons orbit the nucleus, which is made of protons and neutrons. The electrons pass photons back and forth to the nucleus, and that's what holds them in their orbit. That's the electromagnetic force. So then within the nucleus, the protons and the neutrons are made of even smaller particles. As we'll see later, ultimately string theory says all of these quantum particles are made of the same kind of fundamental strings, which are wrapped around compactified dimensions of empty space down at the Planck scale, but we'll get to that. Point of quantum mechanics, the weak and the strong nuclear forces are the forces that bind the protons and neutrons together. So let me just read. Weak and strong nuclear forces. Quantum chromodynamics. That's the field of physics that studies the weak and strong nuclear forces. Quantum chromodynamics. Weak and strong nuclear forces hold the nucleons, protons and neutrons, inside the nucleus of an atom together with a quark, this is a quote from Susskind, with a quark replacing the electron and the gluon taking the place of the photon. So in an atom, the electrons pass photons back and forth with the nucleons, the protons and neutrons, and that's the electromagnetic force that holds those electrons in the atom and prevents them from flying off. Inside the nucleons, the quark replaces the electron and the gluon takes the place of the photon. So like I said, we don't need to get into all the details. In the beginning slides of this entire class, I said we're going to forge a path through the forest of philosophy, cosmology, and physics. So there's so many details. We're just trying to keep on a narrow hero's path towards perceiving ourselves as immortal heroes performing our cosmic heroics for an infinitely powerful and eternal God. So with that said, let me just continue. Special relativity explains the absolute speed of light, and then general relativity explains the force of gravity. A major theme for this class, for my book, is that quantum mechanics and general relativity need to be united. That's what physicists want. That's the grand unification that they seek. But the other three forces are described by particles being passed back and forth with each other. So where's the quantum particle that carries the force of gravity? If you look to this image on the left, up in the right-hand corner of that image, you see a graviton. So that is an empirically unobserved prediction of string theory. It works mathematically, and they discovered that a graviton, was a closed loop of string, carries the gravitational force. We're not going to focus on that right now, but that's the goal, how to unite quantum mechanics and general relativity, and that requires detecting the particle that carries the gravitational force. It only works mathematically with holographic string theory. Quantum vacuum, particle-antiparticle pairs. All quantum particles create their own antiparticles in what is known as the quantum vacuum. The constant creation and immediate annihilation of those virtual particle-antiparticle pairs produces what is known as vacuum energy. According to Susskind, the fluctuations of the quantum vacuum are created by the fact that, quote, all possible paths contribute to the probability for the particle to go from A to B, unquote, which is a result of the Heisenberg uncertainty principle that we talked about a few slides ago. There are infinite paths describing possible particle trajectories in an atom. So we just discussed the force-carrying particles inside atoms and inside the nuclei of atoms. Those photons between electrons and the nucleons could follow an infinite number of possible paths, and each one of those potential paths of these particles being passed back and forth within an atom has energy. And so that leads to the idea of an infinite amount of quantum vacuum energy. The entire concept of vacuum energy emerged in the 1930s, and it's been a source of contention among physicists ever since because, as we'll see, the mathematical equations predict an infinite amount of vacuum energy. And infinity is a number that throws all equations out the window, so physicists try to eliminate infinities from their equations. A nightmare beyond comprehension. Infinite energy of the quantum vacuum. To their dismay, physicists calculate an infinite amount of energy in the quantum vacuum. To tame the calculation-paralyzing infinities, physicists came up with the process of renormalization in the 1950s. According to the physicist Heinz R. Pagels, If someone could actually put on an infinite amount of weight and then reset the scale by an infinite amount to give a finite weight, then one gets an idea of the amount of cheating or renormalization required in the calculational procedures of quantum field theories. The cheating process of renormalization works when special relativity and quantum mechanics are combined, but fails catastrophically when combining quantum mechanics and general relativity. According to Michio Kaku, you get an infinite sequence of infinities, infinitely worse than the divergences of Einstein's original theory, that's special relativity. This is a nightmare beyond comprehension, says Michio Kaku. In the book, I say what an atheist like Michio Kaku calls a nightmare beyond comprehension could be a dream come true for a theist trying to detect evidence for the infinite God in nature, and I am one of those, so this nightmare beyond comprehension to me is great news, but at any rate, let's just examine what this idea of renormalization means. So, the equations of quantum mechanics predict that there should be an infinite amount of energy at each point of the underlying quantum vacuum. Underlying every point of three-dimensional space is this zero-point energy, that there's an infinite amount of it everywhere. Yet we're going to see that the cosmological observations indicate that the vacuum energy must be infinitesimal. It's not quite zero, but it's almost zero, which Susskind's going to describe as the mother of all cosmological problems, but we'll come to that in a few slides. But right now we're studying the history of the gravitational singularity, and the evidence is that there is a gravitational singularity underlying every point of three-dimensional space in the quantum vacuum. And that to eliminate those infinities, they came up with this mathematical process of renormalization. Quantum vacuum, infinitely dense with tiny black holes. To say that there is an infinite amount of energy at every point of the quantum vacuum is the same as saying that the vacuum is made of singularities, or in other words, tiny black holes the size of the smallest unit of spatial measurement, the Planck length. So that's 1.6 times 10 to the negative 35 meters. So that's billions and trillions of times smaller than the nucleus of an atom. We do not have the technology capable of creating energy wavelengths tiny enough to peer down that deeply into the smallest realm of nature. Physicist John Gribben concludes that empty space may be made up of black holes the size of the Planck length packed tightly together. According to Susskind, the world at the Planck scale is a very unfamiliar place where geometry is changing, space and time are barely recognizable, and high-energy virtual particles are perpetually colliding and forming tiny black holes that last no longer than a single Planck time. So this Planck unit, it's named after Max Planck, a German who came up with the idea of this fundamental unit of measurement. I was reading it before this video. It's complicated and I don't want to get into the details. Also, most people call it Planck time or Planck length, but I call it Planck because, for one, I was corrected when I called it Planck length at the California Institute of Integral Studies, but also it is named after Max Planck. So in honor of his name, I'm pronouncing it Planck. So picking up from there, the point for this slide is that the quantum vacuum is made of tiny black holes. We're studying the history of the gravitational singularity, the history of the physics that describe the gravitational singularity. Here, with the discovery of the quantum vacuum energy, we realize that black holes are everywhere. Miniature tiny black holes. And Susskind says they last no longer than a single Planck time, which is some billion trillionth of a second. And that's a perplexing idea because singularities are outside of space and time, and yet black holes can come into and pop out of existence in an infinitesimal fraction of time, extremely temporary as opposed to eternal. Well, the singularities are eternal, but their manifestation within black holes in space and time is not eternal. It's a confusing point, but the main point to identify is that this class is based on the equation psyche equals singularity. And singularities are everywhere. We'll discuss in a few slides Leibniz's principle of the identity of indiscernibles, which says that you cannot differentiate one singularity from another because they're structurally identical, a mathematical point, and they're outside of space-time, so you can't differentiate them by their positions in space and time. I know this is confusing, but we're forging our way through the forest of physics, keeping in mind the goal of perceiving ourselves as immortal cosmic heroes performing on the universal stage for God. I hope you are enjoying this hero's journey into the realm of philosophy, psychology, and physics. If you want to help me create more content like this, please subscribe and consider sponsoring me here on YouTube. You can also click the link to my website, psycheandsingularity.com, to sign up for a multiple-choice test with over 100 well-crafted questions related to this class, and links to the specific parts of each video where the answers can be found. If you take that test to the end, you will receive a certificate indicating that you have become a Psyche and Singularity scholar. In addition to access to that test, there is also the opportunity to answer essay questions that ask you to relate concepts covered in this class to your own hero's journey. I will personally respond to each of those essays, point out any other parts of this class that I think might bolster your plan. Finally, I want to point out that this course is sponsored by the Platonic Mystery School of the Divine Infinite Being, and you can check those guys out at divineinfinitebeing.com.